All right. So I'm going to jump away from talking about motors and jump into talking about how you drive motors, which is power electronics. Okay. Before I do that, we're gonna finish up the example from the other day on DC motors, because it really gets into what you're doing in problem 4 on the current homework. Okay. So the other day I went through the example and we did the introduction to the DC motor. It basically came out with two sort of results, right? If I want the motor to go faster, what did I have to do? More voltage, increase voltage, and it goes faster. If the motor needs to produce more torque, what do I need more of? Current. All right. And again, people don't always think about that current part. Like I said, the example I always think of, people always ask me when they're doing senior design, what kind of power supply do I need? How much power do I need? They'll say they need 12 volts, right? The amps part is important too, right? And unfortunately, you don't see that as much, right? When I'm designing a motor, you have to think about, well, how much torque do I need? So in designing, and I should be careful, not designing a motor, but choosing a motor for an application. Usually a mechanical engineer is telling you how much horsepower you need. And then from there, you can size a motor to meet the requirement. Okay, so let's go into the DC motor example a little bit further here. And this, I said, was the full-blown circuit model that you might have. All right, there's two pieces here. One is this piece on this side is what I call sort of the armature. And then this piece over here is what we call the field coil. And I from these slides, I removed the picture where I had sort of the C-shaped coil or core with the rotor in the middle of it. The big thing with the DC motor, right, was that we had that thing called the commutator, right, where there was a so I had the little version of it here the other day. I think I should still have it here. Maybe not easily accessible, but if you remember, when I took this thing apart here, basically what you have is a rotor that was inside of it, bunch of windings on the rotor, and then there was a magnet on the inside of this. So this is sort of the most general case, right? There has to be a field that basically a field that's created inside the machine that pulls on the rotor to make it move. All right. And we said we needed more current to make more torque. All right. So this is our basic circuit model. And these are the two key relationships that we have, right? Which is that the torque produced by the machine, right? What I always write is T sub E, the electrical torque. The torque produced by the machine is this constant K times the current. And then what I call the back EMF voltage, that's basically this voltage source inside the machine. That's what BEMF means. All right, that voltage is K times the speed. Okay. Now, if I look at this circuit model here, this actually looks almost exactly like the circuit model for the synchronous machine. The thing I didn't include in the synchronous machine is I didn't really include a resistance. All right. Now, in problem 1 on the homework, I do have a resistance because the real machines can have a resistance. And so you should have seen that like your predicted angles are a little bit different than what you predicted them to be. And that's because there is some real resistance. They're not hugely different, but they're a little bit different. All right. So in this case, it looks pretty similar, except I said with the DC motor, I usually end up ignoring L. And I'm going to look at why that is briefly today. That's not something we need to think about too much, but usually we end up ignoring it. Okay. The problem that I gave you in the homework has what I call a separately excited machine. And, it assumes that there is a current source that's driving this field coil. And again, it doesn't have to be a current source. It could be a voltage source, right? And that voltage source would be just, V divided by R here would be whatever the current is going through that coil. Okay. All right. So we're going to look at an example here, but one thing I want to, I talked about for the induction machine, a torque speed curve. For a real motor, you often talk about the torque speed curve. So what that means is torque produced electrically versus whatever the speed of the machine is. All right. So if my circuit, here's how I analyze this thing. I say I put a voltage source V sub A onto this motor. And then inside of it is this dependent source, K times omega M, like that. And then IA goes in. Right? So if I'm looking at this thing right here, I can derive what that torque speed curve is going to look like. All right. And if you got all the way to home problem 4, then you saw me referring to something called the stall torque, right? So what do you think is the speed I am at when the machine is producing its stall torque? 0. Well, the speed is going to be 0, right? I think that's what I asked. I said, what's the speed going to be? Yeah, it's stall. Basically, the motor is not operating, right? Or it's not spinning. It's operating, but it's not spinning. And that could happen, right? If I took that motor I was doing the other day, I could get it to stall, right? By basically just grabbing the shaft of the machine. And if I grab hard enough, it'll max out, okay? So, for instance, I mean, I guess I could. Let me try that just to make sure you guys look with the motor. It'd be pretty easy to try this out. All right. So I take this motor here and let's turn this on. It's not going to work on the setting I had it the other day, but I can change it up a little bit. Let's see. Do is go to, all right, let's try this. So, all right, but plug the motor in to this particular source and hook it up to the right terminal. All right. So if you're close enough to this, you can see it. Right now I got 2 volts on this thing, and it says it's drawing 0.16, 0.17 amps. So if I grab the shaft, the current should go up. And it did. But what also happened? It is basically maxed out now at about 0.8 amps. Now the reason it's maxed out is basically because the power supply can only provide 0.8 amps in the setting that it's in right now. So apparently whatever I'm grabbing this with, the motor is stalled. It's putting a heck of a lot more current in than it was before, because it's trying to produce as much torque as possible to get this thing moving against my fingers. So if I let it go, it'll start spinning again. Because now that the load torque on it's significantly reduced, right? And if I, what would happen if I increase the voltage on this thing? Well, it'll spin faster, yeah. So take it to 3 volts. It's spinning faster. Now, if I grab the shaft and make it stop, what do you think the current's going to do? Yeah, so it hits 0.8 again, right? The reason it's hitting 0.8 is because that's the maximum current that I think this power supply is going to give me. All right, it's hitting its limit no matter what voltage I put on here. It's spun faster, but the maximum current that this power supply can never give me is 0.8 amps. All right, so because of that, I can easily stop the machine. Right, this is basically a stall condition that I've got right here. Right, the machine is totally stalled out. It's producing as much torque as it possibly can, but I have put more torque than that on this thing. All right, so it won't go any faster at this point. So, where do you think the maximum torque is going to be then? So based on what we just saw, there was free spinning, no load on it. The current was about what, 0.2 or a little bit less than 0.2. And then when I grabbed the shaft, the current was like at 0.8, right? So where is the most torque going to be produced? At what speed? 0 speed, at stall, right? How can I figure out what that current or what that torque is going to be? At stall conditions, looking at this circuit, what's omega M at stall? 0. So that means at stall, this circuit basically becomes VA, RA, and what happens to this K omega M? It's 0, right? If omega M is 0, then that dependent source becomes a short, right? So my current here is just VA divided by RA. So IA equals VA divided by RA. This is at stall. So the torque that it makes is K times VA over RA. Now, what would be the smallest torque I ever produced? Well, the smallest torque I could ever produce would be 0, right? And that would happen if I could get the motor to its absolute maximum speed that I could ever get it to. Now, if I have, what would that maximum speed I could ever actually get this thing to? What would that be? What would be the maximum speed as a motor? What would be the maximum speed I could ever get this thing to? Looking at that circuit, what's the maximum that K omega M could ever be? VA, right? Basically, those two could match each other, and there would be no torque going in, or no current. Well, no current going in, meaning there would be no torque. What condition would that be? From the mechanical perspective, what condition would it be where this guy reached his full value? What would the load have to be on the machine for that to happen? What's that? The load would have to be extremely small. Basically, the mechanical torque would have to be 0. There would have to be no load on the machine, right? So it's producing no torque, meaning no current is going in. These two would be exactly equal to each other, and no current would flow into the machine. That doesn't happen in reality because there's always got to be some torque from friction and stuff like that. All right, because we know that I said for this thing to work, there is a direct connection between the outside world. There were those little tabs, right, that touched the rotor. So there's always some friction. All right, but in an ideal case, it would basically be a straight line right here, where this would be omega max, I guess, like that. Okay. Now, what would happen if in theory, if I increase the voltage on the machine? What happens to this curve if I increase the voltage? Well, yeah, so basically, I guess the whole thing's going to shift upwards, right? So the whole curve would go upward. If VA increases, the whole curve changes. Okay. Now, the thing that I also did, and it's summarized here, right, is I said if I have a field controlled motor, I can change what K is by changing the field current. Okay, so if I increase the field current, if I double the field current, I double the K value. So what would that do to this curve if I doubled the K value? Well, so it would, so for, if I had, let's say for K equal to 1, let's say I had, this was my torque speed curve for K equal to 1, where would it go for K equal to 2? Well, basically it would be double that, right? So let me draw that better. It would be double. So this would be for K equal 1. This would be for K equal 2. And if we want to understand where the machine operates, it basically operates at whatever point where the load torque curve and the machine torque curve intersect, right? So in general, right, like what I would have is that the load torque, right? Let's just remember our basic relationship, right? What governs the mechanical side? Well, it's Newton's law. J d omega m by dt equals tau electrical minus tau mechanical. So there would be some tau mechanical curve, and wherever that curve intersected with this tau e curve is where I would operate, right? So if there's no load, my tau e curve would basically be right here, and they would intersect right there. When I'm putting my finger on the shaft, I must be putting a tau e curve that's right here. Okay. In the homework, I do give a case, I think, where the torque that I say is being applied is greater than this point, right? And you'll solve for that, and you'll see that it's greater than that point. Looking at this equation, that sort of implies that what's the motor going to do? Yeah, turn in its direction, right? Is actually what it would do, and it cannot do that, right? If I have no idea how much torque I was actually applying when I have no clue how to measure what that torque would be when I grab my finger on it. I was probably putting more torque on it than I could actually get out of this power supply, right? So it was just fighting me as hard as it could, but what I was doing was not actively making it spin the other direction. Okay, So if you run into a situation where the load torque is greater than the maximum torque it can produce, the condition you should consider is it's producing the maximum torque. All right. All right. And there is a problem like that, I think, in problem 4. Okay. These problems are pretty straightforward to analyze in general. We're gonna work at an example here real quick, but in general, they're pretty straightforward. All right. So all right, let's look at an example. So and it's going to motivate our power electronics thing here in a second. So I said we had a motor the other day. I started this example and I said, let's say that the motor was tested at 400 RPM. And it was operated as a generator. So basically we spun it at 400 RPM and I measured an open circuit voltage of 2.7227 volts. All right. So what I'm going to do is I want to operate this guy at 2 different conditions. But first question I have is, if that's the value, if this guy was spun at 400 RPM and I measure that open circuit voltage, how do I figure out the K value on the machine? Yeah. So basically go back to, if I look at the circuit model, all right, this is our basic circuit model, K omega M RA. And for this particular machine, let me also say that RA equals 13.4134 ohms. And let's say the inductance is so small it's negligible. All right, now it's probably not. In fact, there's got to be some inductance. This thing is basically windings on iron. There has to be inductance, right? But we're going to say that the resistance is high. This is a statement at some level of saying that the resistance is probably more significant than the inductance. In the synchronous machine, that wasn't the case. In the synchronous machine, I never gave you a resistance. I just gave you an inductance, right? Because what was the rating on a synchronous machine? Like what kind of, and the problems I've given you guys, what's the power rating on those machines? Like in problem 1 on the homework right now, I know it's like a 450 MVA, right? Machine. What's that guy? I don't know. It was a watt or something, right? So, they haven't done a whole lot to get the resistance down because they don't care. It's a piece of junk, right? If I'm going to output 100 MVA, I want that resistance to be super, super, super small because I want all of the watts that are produced to leave the machine and not get burned up as heat. All right. So it's one thing that's different here. The resistance tends to matter because these tend to be used in sort of low budget kind of applications, right? Your skateboard there, right? As an example, right? We were talking about that yesterday. So basically the resistance there doesn't need to be usually as much larger than the inductance. That's kind of what it means, right? Is that the resistance is bigger than the inductance. Whereas with some of those other machines, the inductance is much more significant than the resistance. Okay. All right. So we know all this stuff. So Stephen basically laid out how we would get our K. If I tested this thing as a generator, it spins up, and I look at VA. VA is the terminal. So basically VA is what I have right here. So just physically, what is this a picture of? This is the motor. Inside the motor is RA and K omega M. They are the model physically of what is behind these 2 tabs. All right. VA is my leads that are connected right here to this power supply. When I'm running this test, I'm basically saying, no, instead what I'm going to do is I'm going to take these leads and I'm going to hook them up to my multimeter. And when I spun it at 400 RPM, what I measured here on the multimeter was 2.7227 volts. Okay. And from that, I can get K. All right. So if I do that, and the key point that he also made is, yeah, we talk about things in RPM, but I would have to convert that to radians per second first, right? So omega test, I guess we do it this way. VOC would be equal to K times omega M, right? Why is that? Why is that the open circuit voltage, K times omega M? In other words, Open circuit voltage would be right here. Why is it K times omega M? Why am I neglecting the resistor? It's open circuit. There's no current flowing, right? There's no voltage drop on that RA. All right, so it's K times omega M. So basically K would be omega, sorry, VOC divided by omega M. So that would be the 2.7227 divided by 400 RPM times 2 pi over 60 to get that to radians per second. And that works out to be 0.065. The key thing is everything is in SI units. And when it's in SI units, that should be in radians per second. So my units here would end up being volts seconds per radian. All right, a weird unit, but that's the units. Okay. All right. So now I say, let's say I use this thing in an application, right? So I'm in a situation where I applied, so VA equals 10 volts. I applied 10 volts to the motor, all right? And the current that I measure is 0.2817 amps, right? And what I want to figure out is what is omega? So what's the speed omega M, all right? And what is the torque that it's producing? All right, I want to figure out those two values. So how do I figure those out? Where should I start? Yeah, KVL will help me out to figure out omega M, right? Let's do the torque first. That one's even easier, right? How do I get the torque being made? Yeah, K times IA. All right. If I go and I calculate that, it becomes a really small number, 0.0184 Newton meters. Now, if you in senior design or some other class, you start looking at speccing motors. If you look at a DC motor data sheet, all right, a lot of DC motor, like the motor I'm showing you now, I found a box of them somewhere. I don't know where I'd get the data sheet for that thing. If you do get a DC motor, if you're purchasing one like for senior design or whatever, you'll be able to find K values usually on the data sheet or whatever. They're not going to call them K necessarily. They're going to call them the motor constant typically. Might have a couple of different names. One of the things it will usually not talk about the torque in Newton meters. Usually it'll be in ounce inches is the most common thing that they specify those in. All right, and you can do the conversions to foot pounds as a measure of torque. If you do car stuff, you'll know foot pounds. All right, and then ounce inches is equivalent, right? Especially for small numbers like this. Okay. All right, so that's the torque that this guy is making. Now I want to figure out what speed he's at. All right, so for that I got to do KVL, right? So basically I look at it, and let me not draw it. What do I draw on the circuit here? How do I draw the circuit? Yeah, two voltage sources, right? One of them is the 10-volt source. That would basically be this guy right here, right? And then the other one is the one that, again, it's not a real voltage source. It's a model for what's happening inside the machine, right? The other one is that K omega. So I put RA, I put K omega M, like that. All right, so what would I do to figure out the speed here? KVL, right? So basically, I get the K omega M, the current. First of all, this is a motor. Which way does the current go? If it's a motor, the current's going into the machine, right? So it's going this way into the machine. When I had a generator, where was the current? Current was going other way into the source, right? So basically, I think of this here, and again, just like the synchronous machine, just a little bit simpler. Synchronous machine had an internal voltage source. That internal voltage source, if I'm using it as a generator, is pushing current out to the grid source. Same thing here, right? I could use this DC motor as a generator if I wanted to. Okay. All right, so I can solve for that. Basically, K times omega M would be 10 minus IA times RA, like that, right? So I could solve for that. Basically, omega m ends up being 10 minus IARA divided by K. Right? That works out to be, if I do the math on this particular case, first of all, if I do this, what units is my number going to be in? Radians per second, right? If I convert this to RPM, it ends up being 914 RPM. Okay. All right. Now, I want to look at if I had an application where this guy was, say, in a speed control. All right. So a very common thing that you might be trying to do is let's say that I want a robot or whatever to move along the path at a constant speed. Okay. What's going to happen if all of a sudden the robot starts to go up a hill? Why is it going to slow down? Well, yeah, it's got to work against gravity. Basically, there is essentially a higher torque that the machine's going to have to produce to fight against the load, right? So the way the operation happens here is if I have, it's all Newton's law that explains all of it, right? J d omega m by dt equals tau E minus tau m, the load torque, right? So TE is K times IA, and the load torque is whatever it is, right? If I'm operating and I start to go uphill, right? That's going to make TM, let's say TM goes up, right? Now the motors, what's going to happen if TM increases? So initially the current is set at some value, right? And let's say TM goes up. What's going to happen as TM goes up to this number? It's going to decrease, right? So basically so IA is eventually going to go up, but initially what's going to happen is TM, it goes above the torque produced by the machine. And basically the net torque here is going to be, this net torque will be less than 0, which causes it to decelerate, right? So what's that? So IA does go up, but how do I see IA go up? If I think about the circuit model, here's my 10 volts. This is exactly like me grabbing the shaft on the machine there, right? So when I grab the shaft, it slowed down. So there's this K omega M. So if initially, let's say he's spinning at that 914 RPM, okay? And then I grab the shaft. That's going to, this basically tells me I grab the shaft, TM goes up, the net torque is going to go less than 0. So what's the speed going to do? Speed's going to drop, right? If the speed drops, what happens to this voltage source here? It drops. So what happens to the current I sub A here? It increases, right? So basically what happens is the speed drops, IA then starts to increase until eventually these guys become equal again. And he begins to operate at a lower speed, right? And we see that when if I think about that torque speed curve, right? If I think about that torque speed, if I say, okay, let's say I was operating with a constant load torque, right? Let's say this was torque load 1, right? Let's say this was in the example I just gave right there, 0.0184 Newton meters, right? If I increase that load torque by grabbing the shaft, this guy tells me that, okay, he's going to intersect right there. Now, if I have this, let's call this TL2, some higher value. They're going to intersect at this point. What's happened? The current's gone up, the speed's gone down. Okay. Now, you guys follow that basic concept? I mean, what's going on is you increase the load torque. So I increase what is needed mechanically. And so what ends up happening is electrically, I now have to push more current into the thing to make it do more stuff, right? This is electromechanical energy conversion is what's happening, right? So the mechanical side does something that causes the electrical side to react, All right. Well, so, and that's a great, what a feedback system, if I make a feedback system, I can start talking about nature's feedback in this, and there is some natural feedback in this system. But if I'm going to make a control system, I use some feedback to say, if my load torque changes and the machine slows down, I want to do something to make the machine speed back up again. So I'll use that robotic example, right? Let's say I'm going at a constant speed on a flat surface, and then I start to go up. As I start to go up, the load torque is going to increase because of gravity. What's going to happen to the speed? It's going to decrease. But if that's not acceptable, right? And you think about cruise control in a car, right? If a car has cruise control, you start to go up the hill, your car is going to initially start to decrease its speed, but it's going to react to that. It's going to see that it's decreased and it's got feedback. It's going to now try to increase the speed again. So how do I do that? So let's say what happens here is I'm going along 914 RPMs and I had this load torque on the machine. Let's say the load torque increases. All right, let's say the load torque goes to 0.035 Newton meters. What we know is going to happen is this thing's going to slow down. But let's say I don't want that to happen, right? But let's first look at what's going to happen initially. So 0.035 Newton meters. I guess I roughly doubled it, right? Because I was operating at about 0.0184, roughly doubled it. So what do I expect the current to do? Roughly double, right? If the torque went up by a factor of 2, the torque produced by the machine is K times I. So if the torque goes up, current's going to go up by a factor of 2, right? They pretty much just match each other 1-to-1. All right. So I get this now, and I still have a 10-volt source, right? So let's say I got 10-volt source, and I have RA right here. And then I have this K omega M right here. The speed should drop. Probably going to be about half the speed if I had to guess. But we can check that. All right. So let's see. What should I do if I want to figure out the new speed? So I want to figure out the new speed. I know the torque has gone to 0.035. Now I want to figure out what the speed's going to be. 2 kVL again, right? Well, yeah. So proportion of the change in torque. What's the change in torque done to the current? It's increased it, right? So how can I figure out the new current? Well, once I'm in steady state, what has to be true about the load torque and the torque produced by the machine? That's be equal, right? So this is equal to, in steady state, K times IA. That's a steady state thing. In transient, no, but I'm not asking you transient questions, right? So in steady state, they're equal to each other. So that tells me that if I do the math here, IA works out to be 0.5385 Newton meters. Not Newton meters, what the heck am I talking about? Amps. All right. 0.5385 amps. Roughly about double what it was there, which is what I would expect because it's about double the load torque. Okay. Now, how do I get the speed from that? It's KVL again, right? So with KVL, I see that, K omega M has to be equal to 10 volts plus IA RA, right? 10 volts minus IARA. Yeah. Okay. If you do, so in other words, because the current's going this direction, hopefully you guys are comfortable enough with the KVL on that, right? That would be the way it would be. Okay. You can write it better than I did. All right. So omega M ends up being 10 minus IARA divided by K. If I do the math on that, it works out to be about 408 RPM. All right. So if the torque increased like this, the machine's going to slow down. Well, let's say I don't like that. Let's say, it's like my cruise control application, right? If the omega M dropped, the speed dropped as I started going uphill, but I don't like that. what do I need to do to make it go back? I need feedback. I'm going to need the control system that's going to do that. Like, thinking about the control system is a little bit of a tricky thing to think about, but just intuitively, looking at that system right there, this is my model for that system. What do I need to do to get this thing back to 914 RPM? Increase the voltage, right? This voltage is this guy, right? He's got a knob. I can just turn the knob up, right? If I turn the knob up, that's basically going to make omega M go back up, right? Just by KVL, if that got higher, this will get higher. Well, that's kind of odd, isn't it? Why does this go up if this goes up? Shouldn't the current change? Current's based off the torque, right? This is what's going on, and this is true in all the motors that we've kind of done in all the synchronous machine, the induction machine. The load is basically setting for us what the current's doing. All right. The load is setting for us what the current's doing. So that's the thing that's weird about this. Unlike, your typical sort of circuit analysis you're used to, I just look at the circuit and whatever happens, right? There is basically the mechanical side is setting what that current's going to be. All right. So in other words, in this case, I know that this current now is 0.5385. And I can solve for what the voltage needs to be. All right. So I would look at it like this instead, right? So if I had VA, RA, and this is K times omega M, IA is here, and let's say we know that IA is, what do we say, 0.5385 amps. What do I need to do? So I want the speed to be omega M equal to 914 RPM. All right. So what do I do? How do I figure out what I need to do in that case? Well, KVL, and what's my unknown that I'm solving for? VA, right? Basically, I have the VA is equal to IARA, which is fixed in this case, because IA has been set by the mechanical side, plus K times omega M. And I know what I want my omega M to be is 914. If I do that math, it tells me that VA needs to be 13.44 volts. Right? So if I increase the voltage, now the speed goes back up to where it was before. All right. Now, what does that mean? That also means there's more power going into the machine because I got more volts, more amps. There's more power going into the machine. But that makes sense because there's a lot more torque going into the machine. Okay. That's basic operation of the way you think about a motor. So this is, anytime we talk about the term of a motor drive, right? So if you guys, where does this sort of happen, right? So some of you guys in senior design or in other places, right? You probably use like an Arduino or something like that, a microcontroller. They typically have the microcontroller then connects to some other device, which has got transistors. That device with the transistors is what I call the motor drive. And the Arduino is basically telling that motor drive what voltage to apply to the terminals of the motor. All right, that's the basic kind of premise. Now, what I want to think about real quick is, all right, what the heck is that Arduino and that motor drive doing, right? How do I make it? Well, it's adjusting the voltage, right? So I started out with 10 volts, and then I went to 13.44 volts. How can I make an adjustable voltage source? What's the basic idea for making an adjustable voltage source? What's that? Yeah, there's some amplifier that's there, right? So let's just taking a step back from this for a second. Let's just say there is in any kind of motor drive and like those little shield devices, ultimately, when you build your robot, right, you got let's say you got a 12-volt battery, right? And then what's connected to the motor let's call this V motor, right? Or well, this would be VA, the voltage applied to the motor. Right, so I have a fixed voltage in and a variable voltage out. How do I make a variable voltage? Can I use a transformer? Well, yeah, so you're jumping ahead to me. He's going to PWM. That's what we're going to do. Why don't I use a transformer? Isn't a transformer simple? Why can't I use a transformer to do it? It's DC. Well, so what's wrong about that? There's no changing magnetic field that comes from DC. Right. So in other words, if I put 10 volts on the primary side DC of a transformer, how many volts do I get on the other side of the transformer? 0. Right. If I put 10 volts AC on one side of a transformer, the turns ratio tells me what's on the other side. Right. But that was all predicated on Faraday's law. I had to have a changing magnetic field passing through the other coil. If I have a DC current and a DC voltage source, there is no changing magnetic field. Right, the magnetic field from a DC current is going to be constant, right? So there is no way to get a transformer to work here. Transformer is nice though because it's very highly efficient, right? We did that. You guys had problems with that earlier. The efficiencies were 90+%, very high. All right, so DC. How do I make a DC variable voltage source? Well, I did it here, right, with a knob, right? So somehow there's got to be a way to do it. Now, there's one way I could do, right, would be to say, well, let's do this. Let's put a potentiometer in here, right? That would work. It will work, right? I could make a variable voltage source, VA, by just adjusting that. Because at the end of the day, if I put the motor here, basically the motor is just some resistance and everything like that. So if I change this R value right here, I would make a variable voltage source. Totally would work. What's bad about this idea? There would be losses. Yes, there's going to be heat in that resistor. All right. So you're exactly right. The idea that I want to use is pulse width modulation, and I want to exploit what I call low pass dynamics. All right. So I want to understand sort of the basic idea of that motor shield. And how it operates, right? So to understand it, that's why I got my little flashing LED. All right. So I got my. That's a lot quieter. I thought this guy was on making it. So this guy here, I got this green LED here. All right, just flashing, and I am driving this guy. If I looked at it, I am driving it specifically with a square wave. And I am putting a square wave on it that looks like this. 5 volts. And then 0 volts. And then 5 volts. And just repeating it. All right. And the period of this thing, T, which is 1/f. Right now, as I have this set up, F is 1 hertz. Right. So basically what you're seeing is this guy is on for half a second and then he's off for half a second, just flashing like this. All right. Now that makes good sense, right? 1 hertz, just like I have here. You see it, then you don't. You see it, then you don't. What happens if I increase the speed? What are you going to see if I increase the speed on it? More flashes, right? Yeah, so that makes sense. More flashes. Let's go up, not that slowly. Let's say all right, so now I'm at 4 hertz. So yeah, it's faster, right? Now I'm at 13 hertz, faster still. If I keep going, still flashing, right? But do you see it flashing? No, right? So are those. They're all flashing too. All those lights are flashing on and off, but you don't see them, right? Why not? Yeah, the frequency is too high. Basically, the frequency is too high for your eye to see it, right? What's your eye doing? What's your eye? It's a low pass filter, right? Your eye is low pass filtering what it sees, right? This is the way a movie works, right? There's a series of still images that are passing by your face. That if you pass them by slowly, you see still images. But if you pass them through fast enough, you just see the average of it. So right now, what you're looking at is the average of that. So how could I increase the average? So this is the waveform I'm applying. Now I've changed, what am I at? I'm at 125 hertz. All right. So that means essentially the waveform looks the same, it just got tighter. Okay. So this is 125 hertz right now. I don't see the flashing. This is the waveform I'm applying to it. How can I make the average value? So if I increase the average, what do you think the LED is going to do? It would get brighter, right? How can I increase the average of this waveform? Any idea? Well, I could increase the amplitude. That would be one way to do it. So let's get mathy for a second. How do I actually figure out the average value of that waveform? Look at that. All right, yeah. So yeah, so it's the average value. I'm gonna call, I don't know, call this, I guess, V of t. Well, you're going the right direction, right? This is a nice, fun integral to do, right? What's the meaning of an integral? It's the area under the curve, all right? So what's the area under the curve for that integral? Well, except for my drawing being bad, it's a rectangle. 5 volts times, yeah. So and I want to define something here. I'm going to call this, I've got this set up so it's high half the time and low half the time. So what I'm going to do is I'm going to define instead, I'm going to say that this value D is going to be some fraction between 0 and 1. And where I have this sitting right now, basically in this picture, D is equal to 0.5. So high half the time, low half the time. Right? So if I keep it general that way, I'm going to say it's at 5 volts maximum and the width is DT, right? The average value, let me say it this way. The way I write average is like that, with brackets like that. And I should call that V of t. That's the way I should really write that. The average value is 1 over t times whatever that integral is. So what's the area under that curve? It's a rectangle, right? So it would, yeah, height 5, width dt, and boom, boom, those two cancel. And I have that the average value is d times, well, I should write it this way, 5 times d. Okay. So what would happen if d went all the way to 0? Average would be 0 and I wouldn't see it anymore, right? Now I can't do that, unfortunately, with this guy. So what it has, like most function generators, this guy has a duty ratio command, right? So he's set at 50%. So if I'm going to take it down to as low as I can get it, take this down as low as I can get it. All right, so I'm going to drop the duty ratio down. I think I have to hit enter first. So I'm going to do 20%, and then I do enter, which is there. Now you should have seen it got a little bit less bright. Now, if I do the opposite of that, I think the highest I can take this guy is 80%. 80%. Enter. So that is brighter than it was before, right? That's what so if you talk, people talk about LED drivers, right? That's what an LED driver does, is it basically just creates a square wave that goes into this LED to change its brightness up and down, right? It just is a dimmer switch control. And basically it's just relying on the fact that there is some low pass dynamics so that you can actually, your eyes just don't see that variation, right? So that is the fundamental phenomenon that we call pulse width modulation. What I'm doing is I'm changing the width of a pulse to change the brightness or to change the effect that I'm having. And I can use this to drive the motor as well. But to make it work, it's all predicated on this notion of having a system that has what I call low pass dynamics. Like in the case of the LED, it's your eyes. Right? I can flash the LEDs fast enough that you don't see it. Right? And the nice thing about that is it allows me to create a variable voltage source on that LED, right? That would be much better than creating a potentiometer to control that voltage. Okay. So the question is, how would I make this happen? How do I create that motor shield, right? So here's a way to do it. Right. So what I do is I take two switches and I put two switches, one on top of the other. Okay. And that we give that configuration some names, right? But I'm going to say I put those two switches on top of each other. So I created a series circuit with a battery, so V in, right? And then two switches, one on top of the other, switch 1 and switch 2. Now, I'm going to just think of them right now as switches, right? How do I make a switch? What would be a good switch? Well, I can get a bunch of light switches and flip them on and off, right? That's a switch, right? What do I have electronically that can operate as a switch? Yeah, I use something like a MOSFET, right? Now, this is not the transient MOSFETs, right? So transient MOSFETs, how do you guys operate those? Well, you guys make all kinds of small signal amplifiers and you have a good time with that, right? Yeah, a great time. Oh, that's right. So with those things, right, what do? You put little tiny voltages into those. So you put 10 millivolts in and you get 10 volts out and all kinds of good stuff, right? That's not the way we operate these transistors, right? It's the region they don't talk about. It's called the linear region. I'm not going to talk too much about the MOSFET piece of this. But basically, if I take a MOSFET and I take its gate to source voltage and I make it very high, it goes into what we call the linear region. And it basically, when you do that, the switch looks like a short circuit when it's on. Right? Forget all this stuff with GMs and all that stuff. Basically, when I go in, this is for the idiot mode of operation. Guys like me like to operate here. Basically, if I put a voltage VGS onto that thing that's big enough, it's a short circuit. And if I take a VGS off of that thing, it's an open circuit. So it's basically a caveman sort of thing where it's on, off, on, off, on, off. Very simple. That's basically that guy right there is a single bit memory, right? If you go into a RAM, right, in a computer, it's basically just a bunch of switches like that. Okay. And it's a very simple sort of device. This is a very simple digital system in a way. Right? Now, so how is it a digital system? Well, what I do is I take those two switches, S1 and S2, put them in series with each other, right? And what I have over here is this thing called the switch state. All right. So what I'm going to do is when I'll get into one scenario where I have S1 on and S2 off. And then in this period of time, I'm going to have S1 off and S2 on, like that. Okay, so let's consider what's going to happen in this circuit. What I'm doing is I'm measuring VM, which is the voltage basically from the midpoint between those two transistors or those two switches to ground. All right, so let's say I'm in the first period. So S1 on and S2 off. Help me redraw the circuit here. What's that? Short and open. All right, which one's short and which one's open? S1 is shorted, so I have V in here. S1 is shorted and S2 is open. So what's VM? V in. All right, so for a little while here, I have that. That happens to a time dt. Now, when that switches, on, off, I can do the other case where S1 is off and S2 is on. So I still got my voltage source V in, but how do I draw the circuit then? How do I do it? S1 is an open circuit. S2 is a short circuit. That's still VM right there. Right? What's VM equal to? 0. Right? So this guy goes to 0. and then like that. So that is basically a way for me to create a square wave. All I've done is create a square wave with that. And somehow I can control what D is. Now, if you've messed with, robotics or any stuff like that, microcontrollers are really, really good at outputting square waves like this with controllable duty ratios, right? So most likely what I have is a microcontroller that is feeding a signal to these two switches to tell them what to do, right? Whether to be on or to be off. And it makes sure to tell one switch to be on when the other is off. I definitely want to be careful about that because I don't want them to both be on at the same time, right? They're both on at the same time. What's going to happen? Short circuit, right? So that's bad. So I got to make sure they have this alternating operation, right? So, all right, all I've done is to create a square wave. Now, I've made that square wave in theory with 100% efficiency, right? Why is it 100% efficient? There's no loss. There's no resistance in this circuit, right? Basically, when S1 is on, it's a short. When S2 is off, it's an open, and vice versa, right? So in theory, this thing is 100% efficient. In reality, when it's really operating, depending on how it's operating, most of the time, this guy could be 99% efficient, all right? Pretty darn good. But all I've done at this point is to create a square wave. That's not what I wanted, right? What was my goal? Well, my goal was to create another DC value, right? So I started out down this path because I said, well, initially, I had this motor that I put 10 volts on it and it went at a particular speed. Then I increased the load torque. And so the speed went down. I didn't like that. So I wanted to increase the voltage back up. So what I wanted was a variable voltage source, DC voltage source. Have I made a variable DC voltage source? No, I've made a variable AC voltage source, right? But there's some low pass features that I can add to this to get rid of that stuff, okay? So from my perspective, the way I look at this thing is looking into those terminals right there, in other words, looking into V sub M. I can make a Thevenin equivalent circuit looking into there, right? What would the Thevenin equivalent circuit looking into V sub M, what would that look like? You're not used to thinking of something like that where I got switches. What would it be? Well, first of all, what's the Thevenin equivalent circuit looking into any terminals? Voltage source and a resistor, or voltage source and an impedance. What's the voltage source looking into V sub M? It's a voltage source that looks exactly like that figure I drew, right? Voltage source looks exactly like that figure. And what's the resistance? Should be 0 if I've just got switches here, right? So basically the way I can think of this thing is basically that this is my switches. My switches basically become approximated as just a voltage source. And that voltage source is high and then low and then high. DT. And this is Vn, like that. So basically what it's saying is I can think of this thing right here, this set of switches, as basically an AC voltage source of some kind. Now, I'm making another jump, saying, well, I don't want to think of it as one voltage source. I want to think of it as two voltage sources, right? How can I think of anything as two voltage sources? What's that? Well, those three things, basically, I'm saying from their terminals are all equivalent to each other. All right. What am I doing? In that last picture there, I have VDC and VAC. Average value in the harmonics. Yeah, he went there on me, Fourier, right? Basically, this guy's a periodic waveform, right? If he's a periodic waveform, I can think of any periodic waveform. It's periodic because he repeats, right? Any periodic waveform is what? Sum of sinusoids plus a DC term, right? So we can go into the math and write all those. We're not going to write the math down on that, but fundamentally, you guys know what that means, right? There is a DC term this function is represented by a DC term plus a bunch of sinusoids, right? So I can think of that because they're all added together. I can think of this voltage source as being the superposition of a bunch of other voltage sources, right? Basically a DC voltage source plus a bunch of sinusoidal voltage sources, right? So what I've done here is I've said VDC and all the harmonics can be separated out into two different voltage sources. So what would VDC be here? What's that? First of all, what frequency is DC? 0. All right. So what is VDC? Well, it's the average value of that waveform, right? Didn't we just figure out what the average value of that was? D times the max, right? So basically it works out to be VDC is equal to D times Vn. This guy is D times Vn. What's VAC? I don't know, it's ugly, right? I could figure out the math behind it, but basically it would be a zero average thing. Let's do it this way. VAC, just to be real nerdy on it for a second, what would it be? Well, I don't know, it's going to be this. Right, maybe that. Right. In reality, what is that? It's a bunch of sinusoids added together, right? So anyway, I could figure out, you guys have done classes where you figure out what's the C sub K and all that kind of stuff. I don't really care. Let's say, what do I want to do? I want to make a variable DC voltage source, right? And I can easily make that variable DC voltage source if I could do what in this last picture? We did that with the LED here, right? So remember, this guy's flashing, but you don't see the flashing. What is the flashing? The flashing is this part, right? And you're not seeing the flashing, right? So what do I want to do? I want to add a low pass filter that gets rid of that stuff and make sure that I don't see it, right? So in other words, what I want is I want to put a filter here so that all that I see right here at the output is VDC equal to D times Vn. So what goes in the box? Low pass filter, right? All right, so intuitively, what would be a good low pass filter? And how would you design it? So I got a voltage coming in. I don't know how well you guys will be able to take this through. So a resistor and a capacitor. Yeah, everybody's So basically, I could do this. This would be one low pass filter, right? This would be one option for a low pass filter, right? I don't like the losses. Don't like the losses. So it turns out that I have another option, which would be to put an inductor in there like that. All right. Now, if let's say I wanted to check that that's a low pass filter, right? I call this V in. I'll call this V out here. I want to check to see that's a low pass filter. All right. And I want to do that in a simple way. How could I check that? Yeah, so let's check the impedances. Let's say I'm at a low frequency, like DC, right? At DC, what's the impedance of the capacitor? So first of all, Z sub C is what, and Z sub L is what? Yeah, 1 over J omega C and J omega L, right? So if omega is equal to 0, what's the impedance of the inductor? 0. What's the impedance of the capacitor? Yeah, it's open. Right, so at DC, boom, that works. Right? The DC component's going to pass right through that thing. At a high frequency, right? So if omega is really big, what's true about the impedance of the inductor? Yeah, basically it can become an open at some point. What's the capacitor become at a high enough frequency? Short, right? So basically, this is now a low pass filter. Low frequencies can make it through. Now the question is, what's high and what's low, right? That's usually the key point, and that's where the design of a low pass filter, kind of fits in, right? What would be the frequency that matters, do you think, for this guy? Again, you could you do the transfer function, you could find out what's the corner frequency for this guy, roughly, if you had to guess without doing the transfer function. What would it be? Roughly 1 over square root LC on the omega side, right? So in order for this to work, if I don't want VAC to make it through that filter, right? I want it to be disappeared by the time I get to the end at the output. What should I make sure is true about the frequency? All right, and we already did this, right? What did I do here to the frequency to make it? I increased it, right? So I increased it relative to what? I had to increase it relative to something. Increase it relative to basically the time constant of your eye, whatever the heck that is, right? Apparently something less than 125 hertz, right? And that's about right. I think your eye refreshes at, I don't know, probably on the order of like 10 hertz or something like that. Once you get beyond that, your eye really can't see stuff that's happening too fast. All right. So basically what this is saying is I got to make sure that the frequency of this guy here is a lot faster than whatever the cutoff frequency of that filter is. All right. So basically what that means is if, again, the in hertz, right? Because it's easier for me to think in hertz. 1 over 2 pi square root LC, that frequency needs to be much less than 1 over T, the frequency at which I switch this thing. All right, so a common thing to do very often, like in your motor drives, is a couple of kilohertz or something like that. All right. If I do that and set that up right, then what that leads to is my basic DC to DC converter. This guy here is called a buck converter, right? It's if you start learning DC converters, start doing power electronics, there's all kinds of converters, right? It's another sort of Forrest Gump list of these different kinds of shrimp sort of thing, right? There's a whole bunch of them, right? Basically, this buck converter is what I call a down converter. A buck means down, right? It's bucking it, it's reducing it. I call it a down converter because V out's always going to be less than V in. If I built this thing properly, what is V out going to be? What's that? dV in. All right, dV in is what I'm going to get. All right, that's the basic way that I do this. Now, in this particular case, the LC, all right, so these are things that I would have to make, right? And the R, this is my load. So in the case of what problem I ask about in problem 4 would be something like this. LC, and then my motor. This would be RA, and this would be K omega M. Right? That's omega M. That's how you would connect it up. So basically VA would be the voltage across there. So my R here is my load. It's just a generic model for what my load's going to be, right? There's no reason I can't put a motor on there. Now, without me getting into the details on this, it turns out with a motor, I don't actually need an L and a C, right? I could actually do it by just pretty much hooking the motor up directly to the switches. And that's really what you're doing when you have that shield, right? You take that shield, that Arduino shield, and you hook it up to a motor. You don't put an LC in there. Why not? Well, it turns out the motor has its own low pass dynamics, so that if I give it a really high voltage or a really high frequency voltage, the motor only really responds to the average. It doesn't respond to the ups and the downs in the voltage that I apply. Right. But I don't want to get into all the details on that. That's a little bit more detail than we need to get into. Bottom line is this is how I create a variable power supply. Right. And so power electronics are basically in everything at this point. Right. So one thing that you may have seen, right? Maybe you guys, Dayon knows this with me. Maybe if you got a cell phone charger back 20 years ago, would have been this big fat thing, right? And nowadays you get a little tiny little cube, right? How is it possible that before I had to have this giant thing, now I have this little tiny thing? What's different now? Well, it's good thought. I mean, that is true. You can do some things with that now, but it used to be the case that in a power supply, I gave a 60 hertz input, I put it into a transformer, and then I converted the output of the transformer. So basically the transformer gave me a low 60 hertz. How do I go from 60 hertz to DC? So how do I go from a 60 hertz to a DC? What's the circuit that you would have to build? What kind of circuit would it be? A rectifier, some diode circuit that would just flatten it out, right? But it'd be a big fat 60 hertz transformer inside there, right? Nowadays, what do? They basically just take that voltage and just straight away with a rectifier convert it to DC. So it's a big high voltage DC. And then they put it into this buck converter, which operates at a really high frequency, maybe 100 kilohertz or more. At 100 kilohertz, all of my components can get a lot tinier, and now they can fit into that little cube, right? As opposed to that big fat thing, right? So power electronics are really important. And, one of the things I said is, it used to be the case you didn't see synchronous motors. Synchronous motors are a hard thing to use because the torque it produces depends on this angle, and it's a very complicated little device. But with the power electronics, it's very simple for me to start to control stuff, right? This is the simplest power electronics circuit you can get. There's a lot of details I'm leaving out here. S1 and S2 are not switches, right? They're transistors. Transistors don't run directly from a microcontroller. There's some stuff between the microcontroller and the transistors, and there's some feedback to this thing. There's all kinds of different issues, right? Like if I really want that output voltage to be fixed, one thing I probably got to deal with is that V-in is a battery, probably in a lot of cases, and that battery voltage goes up and down, right? So I usually need some feedback to control this thing exactly the way I want to, all right? But again, that's a little bit beyond what I'm going to talk about here. But this is our fundamental concept, at least for how I would create that motor drive. All right. Probably having problem 4 basically is just very simple DC motor stuff. And then it basically says, well, I want to change the voltage. You basically have to tell me, okay, well, what's the duty ratio need to be to get the voltage I want? All right. What you're changing is the width of that pulse, right? And we're just utilizing the fact that if I have a low pass system, I can use this lossless set of switches to put an AC waveform into that thing. And then the dynamics of the machine basically just or the dynamics of my filter here just get rid of all of that AC stuff. All right, that's it. All right, if you got questions on the homework, you can ask me your question.